Hello, my name is Romulus Khalil, and this is my Lab 2 projectile motion. Here's a brief overview. Here's the introduction. The purpose of this lab is to observe a projectile's motion after being thrown, basically trajectory. And the fundamental physics principles we're going to be applying here is Newton's first law and Newton's second law. Newton's first law is basically an object will remain at rest unless acted upon by an outside force. And Newton's second law is the force of an object is equal to its mass times its acceleration. So more massive objects require more force to move. Here is the models we're going to be using: the position update formula, the velocity update formula, the average velocity formula, and the drag force formula. In our experiment, I tossed a paper ball and gave it a typical projectile trajectory. The system was the paper ball, and the surroundings were gravity and air resistance. For tracking the position in our experiment, we used Tracker. Our predicted positions were calculated using 2 computational models in GlowScript, and all of our results were put in an Excel spreadsheet. So here's the procedure. First, we record the paper ball being tossed upwards. Then we put the video into Tracker and track the positions across the time interval. Then we use the computational models in GlowScript as a template for all relevant values and ran the 2 simulations. Then we copied all the results over said time interval into our spreadsheet. So here is our initial conditions. So this is our delta t over here. So 0.1 minus 0.00067, that gave us 0.0333 repeated. Initial position was 0.4883243, which we found by looking here. And then initial velocity was calculated using the model here, the average velocity formula. And as you can see, we plugged in our ball's mass, which we recorded as 0.0045. This was our initial position that we that I pointed out we found in the previous slide. Velocity, same equation as earlier. Here that goes. Where the clock starts, because that's the interval we selected, 0.0667 to 0.1. Delta t, 0.03333, and obviously gravity, and this drag coefficient that we found by trial and error. And then here's our main event loop where we just update velocity, then update position, and then plot that. Also calculating Fnet by calculating Fgrav and Fdrag. Here is what our GlowScript output. You can see the trajectory of the ball is very parabolic. We have these 2 graphs. We'll get into graphs in the next slide. Here are the results of all 3 trajectories placed on a graph. You can see that they're all very similar, which does bode well for our experiment. So here's some possible errors in this experiment. Could have been a bad toss by me. I might have did a bad throw that messed with our values. And Tracker error. It's a software I'm not super familiar with, so any user error is very much likely coming from me. And then here's our discussion questions. Do our graphs predict terminal velocity? The drag model has a nonlinear velocity curve plateauing over time. Where it plateaus at, that suggests that there's a terminal velocity that the paper ball will not exceed. So yes, we do predict terminal velocity. And what if the ball was thrown straight upward? With terminal velocity, would that change? No, the graphs are the same. You can see the output on the left is from straight upward throwing, and the one on the right is from how we threw it in our experiment. And as you can see, the velocity is the same. Conclusion, we can accurately predict a projectile's motion with our models. Actual and expected results were the same, and the only 2 forces that were acting on the ball were drag and gravity. And thank you for watching.